Just a few words about Milosch. Well, he is the responsible for the R&D in the domains of high-power acoustic technologies and sensing systems in the Directed Energy Research Center. But he's also a security researcher. Let's say his expertise is in radio frequency identification, wireless sensors, and ultra-low power sensors. So before joining DERC, he was I think he was also already in the UAE and in dark matter, but he has some very interesting past experience in ARM in the UK. So he was the leader of the research security group at the ARM headquarters in Cambridge. And well, I mean, he was in the IoT security and, you know, protecting from attacks and against malware and, you know, all these things. He is also the co-founder of several high-impact open hardware software projects, including the social patterns, Open Beacon, and Open PCD. So I think there's a lot of things that we have to learn from you, Milosch. So without much more than that, I'll give you the floor.
Hello, everybody. I hope you can hear me. Yes. Welcome to this talk, and depending on time zone, thanks a lot for coming very, very early. So what I want to show you is my journey on how basically I came from software to hardware development and from hardware development to mechanical design, because I'm confident that I think a lot of people of you also have a similar journey or a similar journey ahead. And I want to encourage you to dip your toes into mechanical design a bit, because turns out it's great fun. So as Nicolas already mentioned, I have some experience in creating hardware designs, basically for public sharing and open source and open hardware collaboration. I did some hardware security research in RFID systems. I analyzed and broke some high security RFID cards. But yeah, I also very interested in kind of art and beauty aspects of electronics, and for example was involved in a project where we turned Toronto City Hall into a giant interactive display using remote controlled halogen lights. And yeah, so one of the fun project I was involved in was, for example, the Xbox Linux team, where we ported Linux onto the Xbox and essentially created a subsidized Linux machine that was subsidized by Microsoft, which was also a fun project to be in. So other projects, for example, light painting hardware I developed for Raspberry Pi, like very easy to build. So if you're interested, please check the links of the slides we'll publish after this talk. And one of the more interesting projects I created is kind of like a Docker for microcontrollers, where basically you have the same type of compartmentalization of microcontrollers, and each compartment don't need to trust each other, and you have a similar look and feel as for Docker, but on a very constrained device with very little RAM and flash, like a Cortex M3, M4 microcontroller. So to explain a bit what laser cutting is, what it enables you is to take through an idea and take it basically from your thoughts, turn it, for example, if you're interested in electronics, into electronics, but then test the user experience fully by creating also the appropriate hardware. So when I started software development, I realized that by controlling the hardware, the electronics, I can create much better software, right? Because some of the features are better implemented in, for example, electronics, other features are better implemented in software. So by controlling both domains, electronics and the software, you can create much better products. And the same is true for the third domain, which is mechanical design, right? So by controlling the software, the electronics and the mechanical design, you can seamlessly shift basically the boundary on what features are better implemented in mechanical design, or how to augment essentially capabilities of your hardware or your sensors by mechanical features. And by with today's capabilities, for example, being able to create, for example, design you see on the left within a day or two, send it away for production. There are like beautiful services like EasyEDA and LSC PCB, where you can upload basically your design and get the fully assembled PCB that you see on the bottom left within a week. So while waiting for the PCB, you then already can create with your mechanical design software the hardware for it and test it as a complete product, and also like find out like, okay, like how is the user experience of the finalized things. For example, here you see an acoustic-proof phone charger that we developed. So what you see here is essentially like brainstorming turning into physical objects, right? So the idea was by having like 45-degree angled walls, I can reflect basically a standing wave back and forward between the ends of this box. And by using ultrasound, it would not be audible from the outside. And I can jam the internal microphones in the phone. And while it's charging, the phone with any potential built-in malware can't record anything that is around it. And the angled walls are supposed to prevent escaping of the sound. So there's one thing to have the idea, but the other thing is that I can go just to the MakerSpace and spend 3-4 hours by drawing basically this design and lasering it with the existing lasers. So here I think I use 8mm acrylic, and then just trying it out and see, okay, like, is it convenient? Can I still operate the phone? And so on. So this, I think, is a game changer for the way I work, because I can quickly try out and discard ideas and develop my ideas much faster than it would be normally possible. So the other thing I noticed for myself, it's very, very hard to explain mechanical ideas remotely. So by having the ability to draw basically these in a CAD software, it's so much easier to transport these ideas to, for example, a professional manufacturer that then creates, for example, a low-cost version of the same thing. So here in the top, you see, for example, the same charger, but built into a nice wooden box that you can place on your desk and close it while it's jamming, basically microphone and charging. So the main takeaways for laser cutting is, first, you can avoid supply chain issues, because essentially you work from very, very generic material, which is not specialized at all. So even under conditions like, for example, the COVID crisis, like raw material was still fairly easy to get. So the more specialized your material gets and the more specialized your part gets, the more difficult it will be to obtain these parts, or to the longer the lead times, for example, for these parts will be. So by, for example, being able to create fixtures or test setups from basically generic seed material dramatically brings down supply chain issues. So instead of kind of tinkering my way, for example, let's say with a scroll saw to build, for example, your device from wood or anything, and kind of like having my secret sauce, like which are then my skills for creating stuff, being included in that type of prototyping, by using a laser cutter that does cut out these shapes fully automatic, makes it repeatable. So I can send basically the drawing for this design to a colleague, which is in a different country. They can laser it out within literally 10-15 minutes, and they can repeat my ideas or build and extend on them. So it's kind of like remote collaboration, but with physical objects, and through having this like swift way to manifest these ideas into physical objects with, for example, technology like laser cutting, this collaboration becomes really, really fast. So like you would be in the same room. So the fact that you can laser these parts out quickly also brings scalability. You can share it with 1 person, with 10 person. You can just laser out 10 of these devices, have 10 colleagues build their own device. You can build small production batches for example, having also potential customers to try the device and see how they like it. So this essentially, I think, is again like bringing an idea to a product and not, for example, risking huge amount of one-time costs, for example, for molding and whatnot, to find out that actually the user experience of the thing is just horrible and I don't like it and I need to throw it all away. This risk is pretty much completely removed. And the other beauty is because if you, for example, look at this shape, so the shape is 3D, but the primitives of this shape are 2D. So to draw basically that, I don't need a 3D CAD software. I can draw this in 2D. So this, in fact, was designed in 2D. And this brings basically a very, very quick learning curve. So for example, I have kids that are 8 and 10 years old. So I can give them the 2-hour introduction course that is provided in the tech shop. And they learn within the 2 hours, not just how to operate the laser safely, but also how to draw, for example, simple parts like boxes and hinges and whatnot. And this is not just a theory. So like both my kids had these courses and both my kids were able to do this stuff. So therefore, like, just don't hesitate. Like it's really, really easy. And it's very giving to have access to such technology. And further, I think the main difference of laser technology is that customization is unlocked. So I can, for example, take an existing case, but laser cutouts for connectors in, or engrave, for example, the user interface on it. Yeah? And with the quick production time, I can then have fast design iterations. So I think people keep asking me, what is the difference between a 3D printer and a laser? I think it sounds obvious, but it has some specialties. So whereas in a 3D printer, you don't have many constraints on how to design the device, right? So you can, you have pretty much full design freedom and can have really complex 3D shapes, but that, I think, is kind of the problem of a 3D printer, because managing such data or creating it requires complex to learn 3D software. And I'm stuck with the material that the 3D printer directly supports, which is often have a selection between 2 or 3 materials, and it's just raw materials. So for example, 3D printing on, for example, textiles or something is possible, but I think this is one of the very few cases where actually you would customize the material with 3D printer. But overall, I think very few people use 3D printer for customizing pre-existing parts. Usually you just build parts from scratch, and that's the key problem. So if your part has a certain size, like for example, fist size, it will print around 3-4 hours. If you have like a head size part, I think you are easily 18-20 hours, depending on the print quality. And I think this slows down your design process. But the advantage is you can have pre-assembled parts printed. So whereas the laser, you have basically the sheet already there, so you don't have to print it anymore. You just remove stuff, thus subtractive manufacturing. And because you start off with sheet material in most cases, you can get away with very 2D, very simple 2D drawing software. For example, many of you use or know, for example, Inkscape or CorelDRAW, Affinity Design, Adobe Illustrator. So this is basically as low as the entry barrier is. So in a nutshell, if you can use PowerPoint, you can most likely use a laser cutter to build stuff. So the complexity of the software is 3D drawing software is similar. So the key is that I can have flexibility of material choice. I can use not just like plastic or acrylic or wood, but I can use glass or leather and whatnot. And I can basically customize it with engraving or cutting it. And the print time scales weirdly on a laser cutter, right? So I can print a large part within a few minutes. And like you will see later, I give some practical example, but it's very, very seldom that anything I laser, even complex box assembly with 20, 30 parts, it seldomly takes more than 15 minutes for lasering out the whole thing. So it's like super, super fast. And like single parts, like tools or brackets, you can laser out within less than a minute. So in summary, very low entrance barrier. You can get started with simple 2D drawing software, get involved with that, and then, for example, work yourself up to 3D drawing software if you need it. And the key is you have this very, very precise, reproducible designs. You don't need to have like manual skills, right? So because the laser cutter does the manual skill for you, and it replaces a lot of manufacturing tools because the finishing of these parts is very high quality. So there is very little post processing needed, often only like countersinking holes, if at all, and you can directly assemble your part as it comes out of the laser cutter. So how does a laser cutter work? So if the material is solid, you can set it on fire. You can most likely laser cut it, right? Because the way the laser cutter works is it sets your workpiece literally on fire. But because of the air nozzle, it keeps blowing out that flame continuously, so the part does not burn away. And if you can't set it on fire, you can usually at least engrave it. So, so even, for example, like stainless steel, you can get custom paint where after engraving, you can wash away the paint, but then you have a beautiful engraving even on objects like made of stainless steel. But for example, for anodized aluminium, you can directly engrave on anodized aluminium even with a comparably low power laser. But the most common materials that you would use is acrylic, wood, cardboard. I think is very useful for prototyping, quickly shape or usability of stuff. A lot of people, for example, use it for fabric and leather and engraving of glass. So there are also like CO2 lasers in the kilowatt range, which can be used for easily cutting steel up to inch or more thickness, but these are normally not accessible in makerspaces. So like as far as makerspaces are concerned, you are limited to engraving metal and cutting only plastic and similar objects. So in a nutshell, laser cutter, think of it as a scroll saw, right? So you can cut out 2D shapes out of sheet material plus the engraving, and it does it completely automatically for you. So this is, I think, a nice way to understand what the laser cutter is and what it isn't. So here are some tips and practical applications on laser cutting. So I intentionally start with kind of like casual laser cutting. So for example, here's the examples, which I think some of them are private designs, where, for example, customized like an iPad case made out of leather and engraved it with equivalent of stickers. You see a wood cutout where basically this Bon Appetit sign, which both the outside shape and the engraving is done by the laser cutter. And because the way the laser cutter is designed, like the engraving is not burnt away, but for example, it just exposes the deeper layer of the wood, and the deeper layer of this wood happen to be darker. So you get basically this nice signs with no need of post-processing. So on the right is like this figurine is something that you create during your safety induction course. Even if you know about laser cutters in the MakerSpace in Zeina, you still need to take the safety induction course, and essentially they walk you through the whole process from designing a part to cutting it out, and basically from zero to, for example, something like this design, you will go into this 2-hour process. And as I said, it's kids proof. So if you have any kids, I think they would be very interested in doing such a course, I guess. So here on the left, you see this TI DERC logo, where I did the test engraving into anodized aluminum. And because aluminum oxidizes into aluminum oxide, which is white, the black aluminum anodization turns into this very nice and high resolution logo. And on the bottom right, you see cases that I used for my Open Beacon project where I did exactly that. So this was a laser engraving, and the cutouts happen also to be laser. So therefore the engraving and the cutouts in aluminum were done in one step with just a more powerful laser. So that was extremely convenient to do, and you essentially buy an off-the-shelf case and customize, let's say, hundreds of these front plates within half an hour or so. Here is basically a slightly more advanced view. So what is something underappreciated for laser cutters is that actually they are 2.5D. So in the laser cutter settings, you can assign different laser settings to different colors. And that allows you to, for example, just rest the laser longer on a certain area and do deeper engraving. So here in the bottom center, you see an 8mm acrylic piece on the side. And you see different power settings of the laser result in different depths. So in the extreme, I think with 5% speed and 100% power, you get a 6mm deep hole. And I think this is extremely useful, for example, aligning optics and similar things, because you can create kind of recessed grooves for placing and aligning precision objects like lenses or electronics and whatnot. So even though basic laser cutter is only 2D, like the half D makes all the difference for some designs. So therefore, I highly recommend you look into that. And here in this example, I took just a piece of wood, like a light wood, did a negative lasering in dark wood, just squeeze both of these together, basically because they slot at this point into each other, glue them together, and then you just sand off the light wood, and then you end up with the top center wood block. And after application of lacquer, you get a very nice logo in this case. So what is beautiful with this CD cutting technology, like wood carving would be pretty impossible, because you see the scale of this. So this is like very, very small integral details, and the wood would just chip away if you would try to cut it. But with laser, because it doesn't exert any force on the material, you get like this intricate font details exposed of this logo. So so here is a slightly more advanced case. So here we are still in 2D world. Here is a fixture I needed for my Open Beacon project, where I have basically these programmers that I created, but I wanted to lock them in place more robustly. So I got basically this lever, and then basically with, again, 2D design software, you can then quickly create design that locks basically the lever in place and allows nice operation of this microcontroller programmer. So the key aspects that you keep in mind if you do such designs is it is very convenient to use this tab and slot method, where you create cutouts to align basically perpendicular parts to each other, and then basically just laser out the holes for the screw. So the only thing that needs to be done to assemble this device, so you see this blue outlines around the holes. Blue means in laser language engrave only. And red means cutout. So essentially it would just, for me as a marker, create this engraving marks around the holes. And that would tell me when I countersink basically these holes, how deep to countersink them. So then I can take a simple hand drill and just quickly countersink this 7 holes. And then I can already assemble this device. So the other key thing is materials like acrylic are super brittle. So in order to not have them break at these sharp edges, what you use are the so-called dog bone fillets. So you essentially smoothen the corners by adding these fillets, which is essentially just adding a circle and then chamfering it. And with that, the material becomes super robust. So even under mechanical stress, it does not break easily. The other thing is, the other trick I learned is you can get square nuts. So like this design would work with normal hexagonal nuts, but it wouldn't be as nice. But also like with a square nut, it nicely then sits flush with the acrylic piece, and it has best contacts on both sides. So it's very easy to insert, and it holds itself in place nicely. So these three things, like square nuts, dog bone fillets, and tabs to create basically the 3D structures. So like cutting out, for example, this design should take less than 5 minutes on a laser cutter. And I think this is probably 6 millimeter acrylic sheet material. Yeah, and then basically just using a screwdriver to tighten essentially these screws from the back. So here are some more advanced examples that we created during the citizen science project, where we, with the given sourcing restrictions, which is pretty much like we can't get anything other than like very simple parts like car motors or like wiper motors and similar things. So we tried with these limited possibilities to explore mechanical ventilator designs. And again, like in a team, being there and quickly brainstorming through our ideas and trying them out. I think only with facilities like the MakerSpace, this is possible, but also we were able to iterate and through different designs, discard ideas that turned out not to be very good early, and then ended up within a few weeks with a design that did what we wanted it to do. So here, like I think the memorable pieces of this is, for example, honeycomb structure for the speakers. So the level of customization is just incredible for this technology. And here you see, like, for example, here is an Arduino board on the right behind the back panel. By adding, for example, cutouts, everything is held neatly in place, and something that would be just a mess on a table turns out into nice electronics with user interface and knobs and switches and even a small display to indicate stuff. So like instead of creating a custom PCB, we were able to use breadboards, just neatly put them behind that panel. But from the front, you have this very clean and durable design. And here, for example, the other memorable thing is like in order to also decouple the creation of electronics from the mechanical design of the ventilator, we created this cutout where you just swap out the whole front panel with the electronics behind it as you iterate through the thing. So therefore, like the mechanical designer basically did not have to wait on me finishing the front plate design. So this maybe sounds really scary, but like creating boxes and customizing them is actually crazy simple. So for example, there is this website called makercase.com where you can enter with high depth, and they have different styles of boxes. I think this is the most advanced one with rounded edges, which uses this curve patterning structure to bend nicely around corners. So basically by weakening the wood and allowing it to twist, you can basically have this nice rounded edges. So the website creates essentially, as you see in the top middle, a laser cut file. And at that point, you just take a 2D software and add the cutouts you need, which you can just measure with a caliper. And you can create basically a box for your custom electronics with that in no time, right? And then you can concentrate on testing the whole thing. So this is amazing, and I can highly recommend you like to use these types of websites that generate designs, as you will see later, also gears and similar things. They can automatically generate it. So you don't need sophisticated software to do sophisticated designs. So here are some other prototypes we created. So for example, just to get an idea on how this process looks like, here is the cutout of a gear that we used for one of the early prototypes. And as you see, like I have this idea, I generate this gear online, just add the Excel cutout in the middle. And I have basically this gear in my hand without going to a website, ordering gears and like, dealing with stock issues. I can have it like from idea to I have the gear in my hand within less than 5 minutes. Yeah? The other thing which is like enables a different way of working is like you can completely take the manual skill out by creating fixtures, for example, for thermal bending of brackets you, for example, use for the ventilator project, where you just laser out this additional square, where after heating up the bracket, you place in the square and holds it firmly in place. And so you have a reproducible shape of these brackets. And again, like I don't have to go to weird places to find these brackets. I just make them as I need them on demand. And then basically we can do endurance tests and whatnot with that hardware. So here are other projects that we probably mentioned in the later sessions. So even simple things like, okay, you have a complex electronics and like you work on this for multiple days. Of course, you want to place it on like a tray or something. You want to add cutouts for switches and whatnot, because this enables you to store it away and bring it back, or to transport it between, let's say, the home where you change the firmware, and then you meet your colleagues at the MakerSpace and then integrate it together. So, but this mobility, again, like you cut out something out of laser, just add the mounting holes for some PCBs or similar, and you're good to go. Or for example, on the bottom left, like creating platforms and whatnot, it's completely painless. So here is a more advanced example of this process. So for very like space constrained designs, you're better off if you do a 3D design. So here you see a design that is meant to be placed into a box that you will see later. It's like a fairly complex device. It has a touchscreen, it has a Raspberry Pi, it has a power bank, it has a software-defined radio, and so on. It requires cooling. I need to route cables that should not interfere with each other. I need switches. I need USB charging and whatnot. So I can either basically iteratively design it in 2D and then just accept that I waste like 5-6 sheets of material during that. Or, for example, I can shift all this trial and error into 3D software and design it at home. Basically just then take my laser cut files to the MakerSpace, cut it out and take them again home for assembling the device. So here's basically the same design, just with all the non-laser cuttable parts removed. And modern CAD software has amazing features where I can basically press a button. It arranges all these parts on the sheet size of my raw material that I specify. It seamlessly exports in DXF format, which can directly import into the laser cutter and cut it out. And like, even though this design is fairly complex and like relatively large, this takes only 15 minutes to build that, right? So I can cut it out, try it. If I miss something, I can just cut out that single part again, or cut out the whole thing. So the design process is just beautiful. So yeah, so then after having the parts, basically it comes down to assembly. But yeah, so just maybe nice to mention. So I did not have to model parts like, for example, the fans or the SMA connectors or the switches or the Raspberry Pi. So for that, there is this nice website called grabcat.com where you can download models where other people essentially went through the effort and made these designs. And you have like very nice communities around these pre-designed models. So from assembly perspective, the easiest workflow with the highest reliability came up with is using these aluminium mounting blocks, which are in this case M3. So in the design, you just mark basically the holes. And the only thing you need to add to assemble it is this aluminium mounting blocks. So I will explain later the chamfering. The purpose of chamfering is to increase the precision, because by having this 45-degree angled holes and this countersunk screws, this acts as basically centering help for keeping basically that part very precisely aligned with the aluminium mounting block. And here you can see this Pelican 1200 protector case, which is fairly small. So it's only like 22 centimeters across and like 15 centimeters wide. Basically, you can create this design that nicely fits in that. And the only thing you see on top are the cooling holes and the two SMA connector switch and the USB-C charger. So, and then you have a nice field test device where you can be confident if you take it out for field test that there are no connectors that come off and you don't have to spend hours in setting up your experiment. So one of the things that got my attention lately are this compliant mechanisms. And these become possible with laser cutter technology due to the high precision of laser cutter. So like even like an average laser cutter, you end up with an absolute position accuracy between 10 to 100 micrometers, which is crazy. Even like this was something that even like metalworking, average metalworking was kind of like the best possible you can achieve with simple tools, simple manual tools. But basically having access to something that can laser out something with 10 micrometer precision with no skill needed, I think is again like crazy and amazing. So commonly, like as a rule of thumb, the cut that the laser creates is around 150 micron wide. And so traditionally, you limit yourself to materials down to 10 millimeter. So you can have, with more powerful lasers, you can have deeper or like thicker material, but the quality of the cut will go down. So the reason why the whole system is so precise is the cutting is, you cut, the laser cutter cuts a complete design in one go. So like not just the outlines, but also the holes and everything is perfectly aligned because nothing moves during the cutting and there is no like mechanical force involved. It's just basically light touching the material and removing things without adding force. So that creates this crazy high precision. And this unlocks the possibility of using compliant mechanisms to further increase the precision of your design. So compliant mechanism, as well put by Derek Müller, he has this nice channel called Veritasium, and I highly recommend watching you the video link below. Instead of having hinges and bearings, you just thin the design in selected places and turn that into hinges. So even like brittle material, like for example, acrylic, if you make it thin enough and ensure that you only bend it within a certain radius, then it's flexible and goes back to the original position. So a lot of material has like this hidden feature of being turned into a hinge by just using the right shapes. And that results in, I can basically laser complete assembly from one piece without having to assemble it. So essentially it's assembled by design. So this results in price reduction. You get much more precise motion because you don't have the backlash problems. So for example, like if you move, for example, gear back and forward, there is a play involved. And for example, if changing direction, you would introduce backlash that would drive your precision down. But by using then hinges made out of compliant mechanisms, you can completely avoid that. So for example, this technology is successfully used in space. So where you have the problem to have vacuum, you don't want outgassing or any lubricants in your thing. So you can have higher performance parts. You can make it much smaller because you don't need to add just like dedicated parts like bearings. It becomes more portable and more predictable in operation. So again, like tools like Fusion 360, which is on the high end of design tools, you can just like create this simulation of your compliant device and like play around it virtually, and it simulates the movement. So for example, here, like having this compliant device and having it simulated locally on your machine takes only a few minutes. So you can draw basically any shape or import it and just see like how would it behave if I, for example, apply force, for example, here in this blue arrow, and how does the resulting device move. So you can further decrease the iteration of your design. So if you're interested in that, I highly recommend both of these books. So one is more targeting engineers. It's a practical introduction into compliant mechanisms. They have very nice examples. And if you are interested in the theory behind it, then you want the second book. So here are some showcases of precision designs I did lately based on this technique. So again, basically the full chain, like designing a custom PCB, for example, here a Ccd sensor for a spectrometer, having it sent to production, but while it's basically in production and I patiently wait for a week, I can already design the hardware for it and then create, for example, simple fixtures where I try to understand, okay, like what is the problem? How do optics work? So here in between, actually more steps. So for example, here you see already the optical assembly with the fiber input, the mirror, and the CCD sensor and the concave grating. So before basically putting everything onto one plate, I lasered individual stands for each of these parts with magnets on the bottom, so I could arrange it on my table, figure out a nice setup, and once I was happy, I then lasered this bottom plate to hold these devices in place. So again, I did not have to go to optical website, buy long lead time optical benches, and then because the optical benches are quantized, so I would need then to have complex aligning helpers for the optics. Instead, I here as you see in the left center, I can design the optical path, and this gives me the precise position of all components, and my cutouts with the countersink holes lock my optical assembly into the precise position I want. And then I only have to do fine adjustments in basically in the sub-millimeter and micron level to compensate for the remaining tolerances. So you see here this rainbow projection of the resulting image. And as you will see on the next slide, the adjustment is done with these hex standoffs next to the concave mirror. So, but in a nutshell, you can perform with this workflow a major design change, like changing the focus of, for example, the concave grating, replacing by a different one, just regenerate the whole mechanical design automatically, because this is what parametric design allows. Laser it out within 15, 20 minutes, and have basically the prototype of the changes in your hand in less than 1 hour total. And this is just like, it keeps blowing my mind to have this access to such technology. So here, just a quick background. So here you see a close-up of the Ccd sensor. So the problem here is I have the Ccd sensor, which is just one line of pixels that is 200 microns high. Each pixel is 8 microns wide. So I want to focus basically the optical fiber that went through the grating and split out the spectrum precisely on that CCD sensor, and that would be impossible without expensive alignment tools. But again, like prototyping that with a laser cutter becomes absolutely realistic. So here is a compliant mechanism I used for an earlier version, just to be able to tilt the CCD sensor and to lower it and to raise it. So you see basically the green holes. So these are where the PCB is mounted. And I just use this M2 screws. And by twisting basically these knobs, I can then lower individual sides resulting in tilting, or by moving them in unison, I can lower and raise the whole assembly. And the flexible joints that are designed in counteract that and keep it under tension. And you see like the whole basically gray area, this is one piece, it's lasered out of one piece. And again, like if I need this alignment tool, I just laser it out, and the only specialized thing I need are this M2 screws. And for example, add features like tornado stoppers, so I don't over stress the flex joint, so it stops naturally at this maximum position, so the flex joints survive even mishandling. And yes, on the bottom plate, there is a hole where I guide basically the outside assembly so it doesn't move sideways. So here you see another design. For example, here I have this compressed rubber bumpers, which are used normally for reducing vibrations on assemblies. But here I use them as a quasi-compliant mechanism in combination with adjustment hex dials to align this concave grating mirror precisely. And here basically you see a cross-section of the aluminium cubes I mentioned before. So instead, like the big advantage of aluminium cube over this T-nut design is that it enforces right angles, and in combination with the countersinking, it dramatically increases the precision of your laser cut. And also from a 3D design perspective, it's extremely convenient. You just duplicate these aluminum blocks, keep aligning them, and then there is a built-in function for performing this countersunk drills. You just point it at the side you want to drill it, and it automatically adds on the adjacent part this countersunk borehole. So essentially adding these drills into the 3D design, like let's say 30, 40 drills, is just a question of a few minutes in the 3D design software. So it's extremely convenient to design, but also results in good precision. And here you see basically on the top of the design, you have also these screws. So you can add this lid, and it then clamps all the components from both sides, top and bottom, and increases the precision further. So here, a quick introduction about movement motors. So instead of buying like this ready available, for example, tooth belt gears, you can do much better. So for example, you can laser your gear, but you can also make it a mechanical part. So for example, here you see basically the laser gear, but it's part of a mechanical assembly. So basically my experiment rotates on that plate. So I can basically add this nut and slot structures into the gear in the laser cutting design. Here in the center, you see a slip ring. So the wires you see dangling out on the bottom are USB interface. So I can basically have something that rotates at a high precision, but also I can run USB and it doesn't twist my wires or anything. The motors you see in the picture are super nice. So you can get this Misfit Tech or MakerSpace motors, which have a built-in display for configuration and with buttons. The control is completely built-in, and it measures its own position. So like it won't slip or anything. You can say like rotate by 725 degree left, and it does exactly that even under under load. It's super nice. So, and with that, like creating, for example, such an experiment is completely painless. And again, like there is the like free gear generator software if you don't have a sophisticated design software. So I highly recommend you to check this websites out. So the last thing is, depending on your level of pain you want to experience, and depending on your confidence, there are different options for software you can pick. So like this is software that I all tried by myself. So there is other software that I didn't mention here, but I only want to talk about software I use myself. And my subjective comparison is this. So there's software, for example, the bottom end, which is like, I think, made for kids, is like Tinkercad, where you can create very, very simple 3D designs. But anything practical, I think, is a tough challenge. So you can't create anything complex. But for example, with free software like Inkscape, you can already create a pretty sophisticated design, but you have to experience a lot of pain because some advanced features that you have on the CorelDRAW, mainly around alignment and construction of relations of parts. I think CorelDRAW is super easy, but both software CorelDRAW and Inkscape are 2D, and therefore, like the 3D needs to happen in your head, which is a different problem. But if you have a good perception of 3D objects, then this is, I think, a very low entrance complexity. And then basically you have the ubiquitous SketchUp, which is fairly user-friendly, but you quickly hit a wall on complexity. Like there is this pretty geeky OpenSCAD, which is kind of a programming language, but for CAD. So it's, I think the complexity is very, very limited, but you can do more things than with CorelDRAW because you can do actual 3D designs and can parametric generate things. So Designs for Mechanical is a very good option. It's free. It has limitations which are sensible for makers. And the learning curve, I was amazed the complexity of the design I could create with very little background back then when I started using 3D design software. So Designs for Mechanical was an eye-opener that actual 3D design is not difficult. It's fairly user-friendly. Like even back in the time, it was the most user-friendly 3D design software, but the user-friendliness of modern products, like for example, Shaper 3D, where essentially the cost is mainly you need to get an iPad Pro with a pen. But the user-friendliness and the quick learning curve is just mind-blowing. So I think you sit down with like 2-3 tutorials of them, which will take you less than an hour. And after that, you can already design fairly complex 3D software, even with zero background in 3D design. But then you have a huge gap and nothing, and very long nothing. And then you have tools like Fusion 360 and SolidWorks, which realistically to do more sophisticated design than SketchUp or Designs for Mechanical Shaper 3D, the learning curve would be in the months to use the advanced features of SolidWorks and Fusion 360. And having all the power at your hand is also distracting because like having a software that can do a million things, like it's tough to figure out which of the things you actually need. So this is my subjective comparison. Your mileage may vary, but for me, basically, it allowed me leaving this Dunning-Kruger valley of despair. Yes, oh yeah, like mechanical design is complicated and like only weird people can do it. So turns out actually it's not that difficult if you have a modern design software and it can be actually fun. So this is the end of my presentation. Do we have time for questions?
Well, yes, I think that we can allow a couple of questions. Just to give some hints to the attendees, you might not be able to see a mic or a camera because we did this on purpose to avoid any possible hacker trying to come and disturb our meetings. It has been a problem in the past. So if you have any question, please use the button that is below your screen to raise your hand and we can enable you the voice. Other than that, you could also use the Q&A box that is also in the lower part. So in the meantime, I do have a couple of questions for you, Milosch. Thank you, first of all, for all this comprehensive presentation. I really enjoyed the fact that you're showing finalized prototypes, which is very much in the spirit of this talk. And I'm super, super impressed about all the things that you can do. One usually thinks that laser cutters are only for big things, but the precision that you have been showing today are definitely amazing. I had this question that is still not clear to me from after your presentation. So this is a laser cutter is something that you usually want to have in a big workshop like MakerSpace, right? Or is this something you can host at home? I'm more concerned about the environmental problems that it could have.
I would highly discourage people from buying laser cutters for home. So like the fact is, yes, you can buy laser cutters for like decent quality for like $400-500, right? So the price dropped now to a point that what I would be very, very concerned is just the fumes it creates. So either you eject that into your environment, so your neighbors, if you think your neighbors are angry about you barbecuing, then don't do laser cutting at home, because like you have like this really, really highly toxic, cancerous fumes of your acrylic cuts that you blow out of your window. And washing it and running inside, you create CO2, which is again like not very good for your health. Because like the way it does that, it burns the material. So you have like effectively open fire in your home and like burning plastic in your home. You would not do it, right? No. Even after washing these fumes with very expensive equipment, you still would not want to eject it into your home or into the environment. So I think you're better off in like laser cut is one thing which is better off in a shared space with proper ventilation, high quality air purification, air washing. So yes.
Okay, good. There is one question from Alvaro. He's commending you for the talk, and he's curious about where do you buy the aluminum connector cubes?
So the answer for that is like pretty much everything I bought in my life in the last 2 years. It's all AliExpress. So AliExpress Direct, especially in the UAE, is amazing because it's a flavor of AliExpress that includes not just the flat shipping costs. So like if you buy something for more than $40, it ships for free, but also includes VAT and import charges. So it's directly delivered to your front door. Many of these manufacturers I order now deliver within like 10 days or so. So it's also fairly timely. So especially manufacturers like for screws and aluminum blocks, like that stuff arrives like within a week usually. And like it's very hard to discover such things in the UAE, right? Because there is no good website to go and see a listing of companies. I would doubt that such specialized things you can easily find here. So AliExpress Direct is important. Make sure to filter for AliExpress Direct, because AliExpress Standard can easily take 1.5 to 2 months for shipment. And at that point, I probably forgot that I needed them in the first place when I received them.
Good. Another question from Mohamed Al-Kabi. So he's asking whether there is a way to convert a 3D model to 2D layers, maybe by a slicer, to laser cut them.
Yes, that is possible. I think I've only seen it in combination with artistic projects. So for example, whenever you can take a Tyrannosaurus Rex head, slice it with, I think Autodesk provides such slicers and creates it into like sheets of metal that you can either glue together directly, or you have like this rib-like setup. But for anything professional like a box, you would not do it. So instead, basically, you do it the other way around. So when the box you've seen earlier in the slides for the Palinka case. So what you can do in professional software, you define the thickness of your material as a parameter. And the nice advantage of that is that whenever you create like a wall or anything, you refer to that parameter. So this means that, for example, if you come then to a tech shop and say, oh, they don't have 8mm acrylic, they only have 6mm acrylic, you just change this parameter, your whole model regenerates, and you can, and the tabs and slots are perfectly suitable for the other sheet size. But essentially, the short answer is you design your model from sheets, and that allows the software then to unplug these individual parts, lay them out flat, and you can laser cut it. So I think this is the better approach to control essentially the segmentation instead of relying on some automatic mechanism to do the segmentation for you.
Good. Another question from Ralph. Again, thank you for a good presentation. And then he says, did you get any chance to compare GD&T representation issues in different softwares?
GPNT, sorry, help me.
GD&T.
What is GPNT?
Andrew, is there a way you can give some sound to Ralph?
Sure, I'll do that.
Hi, Ralph.
Ralph?
Hello. Yeah. Hi, Milosch.
Okay.
Hi, Ralph.
Yeah. Milosch, very nice presentation. It's really an eye-opener for all of us here. Just one question about, GD&T, which is basically a geometric dimension and tolerances. You have compared most of the softwares, and you have shown us that, each software basically a level of complexity and friendly user. Modeling, a 3D modeling is always a fancy stuff. When you make a 3D model, it really looks nice. But when you put it in the documentation, like when you put it a real design in the drawings, my question always remains that a GD&T plays a very important role. Did you get any chance to compare that in context of, for example, tolerance analysis, perpendicularity, and other aspects of GD&T?
Yes. So there are basically two answers to that question. So one is basically for professional manufacturing. You have to express to the manufacturer which of the tolerances you care about and which of the tolerances you don't. So I don't think a software can automatically infer that. So this is something that would, in my opinion, traditionally happen in the drawing stage. So for example, even like this software I mentioned earlier, Shaper 3D, and of course, Fusion 3D and SolidWorks, they have this drawing mode. So you basically can create projections of your 3D design, turn it to drawing, and annotate that with the sizes that you expect. And at that point, you would give basically hints to the manufacturer that where you need what tolerances and what, for example, level of perpendicularity and whatnot, so it can be tested later. So I did not do like the automated version, so I think you probably know more about that yourself than I will ever know. But the other answer is from a practical perspective. Of course, these tolerances depend a lot on the material used. So for example, the tolerances for wood, for acrylic, for different thicknesses of acrylic, or different precisions of cutting acrylic. So for example, by reducing the movement speed, I can have a faster, more high precision cut. But at the same time, the profile of my cut changes. So to take all of this account, the simple answer is you would perform a calibration cut, like you've seen, for example, for the 2.5.D engraving. You infer the tolerances, and all advanced CAD software, so I think Shaper 3D doesn't have it, but Fusion 360 and SolidWorks have them. You would essentially not automate the CAM step by just taking the DXF file and throwing in the laser cutter, but you would create an intermediate DXF file where basically the CAD software would add and remove the right level tolerances. So that would not, essentially not require you thinking about the tolerances. You measure tolerances, you put them into the system, and then you create a secondary DXF in the CAM module step that would add or remove the tolerances as needed. So you have a tighter or less tight fit. So from a practical perspective, I think this is probably the way to go, but this is, I think, only an option if you manufacture stuff yourself. But I think for external manufacturing, I think you still then need to express your precision desire. So which parts you intend to have very precise and which not through the drawing, I guess. I hope this answers the question.